Now that I look back on what I've learned in Mr. Trader's class and the fundamentals, he not only taught you math, but he taught you responsibility, being accountable for your decisions and the decisions you've made. And he really teaches you that it's just because you know math doesn't mean you can go out and turn it into something else. You have to really understand it. And I think I've applied that to all of my subjects.
He has this uncanny knack of being able to meet students where they are, regardless of their achievement level. If they're gifted kids, if they're kids who struggle a bit, Mr. Trader takes the time to meet those children where they are, and everybody achieves in his class.
I think that you really need to set a lesson where you can apply it to real life situations and then get the student engaged in applying what they are learning to the real life situations. When you can talk to a child about lending companies $200 million, those eyes become wide open. And I can take that and explain to them that it's nothing more than $20 with just a bunch of zeros. So they can relate to those problems, and I can take everything that I've learned, because as a corporate banker, you are exposed to many different industries, many different companies, and that allows me to take those experiences and put them at a level where those students can relate to and enjoy, because sometimes those eyes are so wide open that they just, it engages them. It makes them want to be able to relate what it is we're going to do.
Today, guys, we're going to do some interesting activities, and we're going to be able to tie what we're learning to those activities. But we have to take a look at what some of our prior knowledge is first. So I have a couple warm-ups on the board that I would like you to do. If you feel good about how you performed on the warm-ups, I'd like to see a thumb up. If you feel bad, I'd like to see a thumb down. And if you're a little unsure, I'd like to see a sideways thumb. Go. This is what you're going to learn new. You have not solved equations with no solutions. You have not solved equations yet with infinite solutions. This is key, and we are going to tie this to an essential question, and we need to be able to answer this essential question before we leave. We are not just going to solve them. We're going to be able to relate it visually, physically, and algebraically. We are actually going to do some activities that will allow you to engage and learn from those experiences. Let's talk about some real-life experiences.
Mr. Trader does experiments and really applies math to your life. It's not just a class, it's the real world applied in his class.
It's one thing to understand the algorithm, but it's another thing to put it into real life practice. And when they can put it into real life practice, they can better relate to it and better remember it.
How many of you remember the first time that you were on a Teeter Totter? What happened on that Teeter Totter, RJ?
I was a real little kid, and I went on with this big guy. And so he sat on one end and I sat on the other. And I went all the way up, and it was kind of scary since I was like 4. And the teacher explained to us about how since he had more weight, he sank down because of like gravity, and I went up because I was much lighter than him.
So you have a real-life application that you've experienced, you've seen. You even have a teacher that taught you some of the concepts that we're going to learn today. How many of you have ever used a wheelbarrow? Brandon, can you share your experience with a wheelbarrow?
The first thing in the lesson plan was a warm-up. When the students came in, I wanted to see if they remembered what we taught them the day before. The second item was the hook. How many people have used a wheelbarrow before? How many people have been on a teeter-totter? How many people have used a dolly? And once they had that tie to a real-life situation, I could take them to the next level.
Let's review that prior knowledge you have and that understanding of solving equations in a single variable, and work the problems independently, but collaborate as you need. Has anyone got to a problem yet where it doesn't have one solution? It looks a little odd.
Mr. Trader, my answer is not on the board, and I did everything right, didn't I?
This looks good. Ah, I see. Okay, and this is a mistake that a lot of people make.
Let's go back. Can I walk through this on the board?
When in his classroom, when he sees that students might be struggling, he will try to create a problem with like a real life situation and have it apply to them individually.
Now we're going to move on to the Learn Zillion video. So if you will start that now, you all know how to get into Learn Zillion. We've used this on a regular basis. This is to help do some self-teaching and you to do some personalized learning.
I use technology in a number of ways. One of the ways is to tie it to another content area like science, technology, engineering. There's a number of resources that you can go out to. Mars is one of them, where you can find those lessons, where you can get interactive and apply them to a science, engineering, and technology, much like we did in our lesson. The other key thing is there's resources such as Learn Zillion, Khan Academy, that you can sign these students up for, and it will go into really identifying what the students know, what they need to know, and self-drive lessons, and they can do it independently.
Let's do a quick summary. Have you learned anything new in this lesson that you did not know? Savannah?
I learned that you can have either no solution or infinite solutions instead of just one. And in an equation with no solutions, both sides equal two different things. And in an equation with infinite, they both equal the same on both sides.
Yeah, very good, very good. Ashley, could you give me an example of maybe what an equation would be with no solutions?
Well, if the equation's answer was -2 = 5, that's not a correct statement or a true statement, so it would be no answer.
Untrue statement, untrue statement.
I think that you really need to set a lesson where you can apply it to real life situations and then get the student engaged in applying what they are learning to the real life situations.
Let's move on. I'm going to give you the activity instructions, but you need a little background before I give you the instructions. We're going to transition those concepts into applications, not just of the Teeter Totter, but also of using a wheelbarrow, shovel, and a moving dolly. And then we are going to go over the assessment of those activities. I'll give you a rubric and a summary report request that you can then submit to me through the Google shared document accounts that you have. So the activity, as we move into the activity, you need a little background. You need to understand that force distance equals force distance on both sides of the fulcrum of a teeter-totter. What sign is this right here? Huh? Greater than. Greater than. Oh, wait a minute. How about less than? Force distance on this side is going to be less than force distance on this side. It's going to be greater on this side. Okay, now let's move down. What is this sign? Greater than. So what do you think? What do you think, Chance? That represents force distance is greater than force distance. Can you explain to me why that teeter-totter is lower on one side than the other?
There's probably either a heavy person on the left side and a lighter person on the right, making it go off skew, I guess. Or you have someone who's lighter, close to the, heavier, closer to the middle, and someone lighter, closer to the edge, and have it go that way.
Yeah, because really, I got two variables on both sides. Do you want to add to that, Cassie?
Well, it doesn't necessarily have to be a person. It can be any type of force. Like you can use bricks or cement or
anything that has force in it.
Exactly. It doesn't have to be a person, does it? And that's what we're going to do today. Okay, we're not necessarily going to be able to do people, although we might, but we're going to use different weights. We're going to use different weights. Now, if you know 3 of these 4 variables, can you calculate the 4th? Yes. Absolutely. If I know the distance on the left side and I know the force and the distance on the right side, I can use this force as a variable and I can actually find the solution, right? Can somebody tell me why this first one looks like the teeter-totter is balanced? Ian?
Because the distance and force are exactly the same, so that's why it's balanced.
Well, I don't know. Do you really know that? I don't give you what the distance is.
Well, because at the end of each teeter-totter there are 50 kilogram weights, and then since the fulcrum is directly in the middle, it just levels out to be.
Yeah, and I sort of tricked you because I didn't tell you. Remember, you can't always look at a drawing and know that it's right, right? Usually they've got to give you information. But in this case, I agree with you. It's balanced because force distance equals force distance. Now, in this particular case down here, it shows the fulcrum a little more to the right. Corey, what's going to happen in that particular picture?
Depending on what the weight on the left would be, it would either tilt right or left.
I like that. You actually hit the nose. You know, you got it right because it depends really on what that weight is. If this weight, has it got to be heavier or lighter to be able to get this to balance? Lighter. Lighter. It's got to be lighter because it's more, there's more distance there. There's more distance there. When we get in there, we're going to break up into the teams that we have, and we're going to set up our teeter-totters, and we're going to spread around the room. So you're going to take your fulcrum, you're going to set your teeter-totter in it, you're going to try to get balanced. I have a number of weights, and I also have a scale. So we are going to measure the weight so we know how much it weighs. We need to be consistent with our measurements. Can I use pounds on one side and ounces on another? Absolutely not. I've got to convert to ounces. You will also have meter sticks to be able to measure your distance. Now remember, you're going to measure it to the fulcrum to where? What's important if I have a weight over here?
You've got to put it in the center of the force.
Exactly. You've got to put it right in the center of that weight. Some of you might choose to put a couple weights on there, right? Okay, but I would suggest that you put them on top of each other so you can be able to identify the center. Are you all good with that?
Yes, sir.
Are we good?
Yes, sir.
Okay, good. All right, let's move on to the activity.
Knowing that I was coming into a STEM program and needing to find something that I felt was effective in bringing science, technology, engineering, and mathematics under one umbrella. And I spent some time with a friend of mine who teaches engineering at the high school. And we were talking about what can be effective for 6th graders, 7th graders, and 8th graders that they can relate to, that they can do hands-on. And he told me about the engineering concept of force distance, as well as learning about compression and tension. And so I developed this lesson plan based upon that knowledge. I've used this in a STEM environment that included 6th, 7th, and 8th graders on an after-school program. And it's allowed me to take the different level of student, pair them up, for instance, an 8th grader with a 6th grader or an 8th grader with a 7th grader, and allow them to support each other as they're learning this new material.
As we learned, force distance is always going to equal force distance. And remember, the force is the amount of weight. So you've got a number of weights up here, some heavy weights, some lighter weights that you're going to have the opportunity to choose from. You're going to set that on one side of the teeter-totter, and you know, because you're going to put marks on your board by inches, you're going to measure starting from 0, which is the middle of your fulcrum, you're going to measure out by inches all the way to the end. You're then going to do it on this side. Again, starting from 0, you're going to move out all the way to the end. The reason is because that way you can identify what your distance is, right? You're going to be able to identify what your weights are, by coming up here and using a scale. We're going to practice here once. I picked on Riley. Riley is going to estimate where she needs to put the weights of bricks to balance this weight on the right side of the teeter-totter. Riley, why don't you take your best guess? Oh, okay, so now I know that if I calculate the distance here and the weight here, the distance here and the weight here, which one's going to have the larger number? Absolutely, not just the bricks, but what side?
Right.
The right. You're right, my left, right? This is going to give me a bigger number than this over here, correct? Okay, good. All right, now remember, you're going to do this twice by estimating, just by moving. Once you do it twice, you're then going to solve the equation. To solve the equation, you're going to write force times distance equals force times distance. Which two are you going to know when you go back? Well, you're going to know the force of both of them and the distance of one of them. So you're going to fill one in with a variable, right? So if I have 20 and my distance is 10, and I know my other weight is, let's say, 10, I'm going to put a variable in for what I don't know. A variable. If I know 3 of the 4, can I solve for the variable? Yes. Absolutely. So you're going to estimate twice, and then you're going to go actually put down what you know and solve what you don't know. Any questions? So let's go ahead and mark your boards. After you get your boards marked, let's make sure that we can come up here in no more than 4 people up here at a time. Do a quick total of your weight. Now maybe what we could do is we could have one of the teammates go ahead and come up and get weights while the other's marking. This looks pretty good, guys. I'm going to throw you off a little bit. Okay, I'm going to add this right here. Okay, and I'm going to put those 2 weights. I'm going to put those 2 weights right there. Now, are you going to be able to measure the center of where those 2 weights are?
No.
Why not?
Because they're not on top of each other.
Yeah, that's right. So what are you going to have to do to that to make sure that you can get measure a center?
Put one on top of each other.
Ah, good. Okay, you want to do that? Okay, good job. Good job. Now we're going to actually move to here, and I'm going to pick a couple people. Chance, I mark this at 25 inches. Could you stand on this board at that 25-inch mark and try to center your weight on that 25-inch mark? Okay, good. Now, I have 504 ounces sitting right here, and we've calculated Chance's weight at 2,256 ounces. How far is Chance away? Okay, so let's see if Riley can improve in setting that 504 ounces on the teeter-totter to try to balance. Unbelievable. Well, not quite. Okay, so how far do you think you might have to move it back?
Probably 5 more inches.
Does anybody think there's enough room on here to move it? It's a balanced chance? Do? Okay, well, let's try it. Might not be long enough. Okay, so what's going to happen? She's at the end. She can't go any further. So what else could we do to get it to balance? What do you think, Danielle?
You can add more weight to the right side of the scale.
Good, you could add more weights too. What else could we do? Ian?
We can move cans back just a little.
Back just a little. You think so? Do you agree with that, Cassie? You can move him back just a little? How many people, thumbs up if you think we move him back a little? Thumbs down if you don't think we move him back a little. Okay, I see, Brandon, you've got your thumb down, so what do you think?
I think you need to move them closer to the floor.
Thumbs up if you agree with that. Okay, some of you had thumbs down and now you went thumbs up. Okay, all right, that's good. So how far do you think you have to move up?
Maybe 5 inches.
Oh, let's try it. Oh, so now he's at 20 inches. Okay, so now I know it's somewhere between 20 and 25 inches, right? How can I actually find out exactly where Chance needs to be?
Multiply force times distance.
Okay, I can multiply, say that again?
Force times distance.
Force times distance. Okay, now we know he's about 20 inches. Okay, if I multiply those together, does anybody know what 2,256 is times 20?
4,500.
Yeah, because you multiply by 10 and then you doubled it. Very good. Very good. So we know this is 4,005, be 45. How about 44,000? No, 45,000. Chance. So we found out that you need to be at about 21 inches. Could you move to where you believe 21 inches is? No, not bad. Pretty close. All right, good job. You all agree? About 21 inches? Very good. Now I have some questions that we need to ask. Zanti, how did today's activities help you relate to these standards?
Well, we learned that force distance equals force distance will make you have a solution. And when the force distance equals force distance doesn't balance, you have no solution. And when there is force distance is equal to force distance, you can also have infinite many solutions.
Great job, Zanti. Okay, good job. Good answer. We've obviously learned relating it to real life. Let's answer the essential question, how can I apply and benefit from a practical real-life use of solving linear equations in one variable, visually, physically, and algebraically, and understand and relate that to the outcomes? Well, we did that visually by looking at the teeter-totter. We did it physically by using the weights. We did it algebraically by solving one of our variables. If we know 3 of the variables, we can find the 4th. Good? Have we covered our essential question? Have we achieved our goals? Now we're going to take it to the next level, because not only can you apply it to a teeter-totter, but we're going to go outside, we're going to apply it to a shovel, we're going to apply it to a moving dolly, and we're going to apply it to a wheelbarrow.
So I took what they've learned, and then we put together and applied it to making the teeter-totters, where they could get weights, they could measure those weights, they could measure the distance from the fulcrum, and then determine whether or not they had a solution to an equation based upon where they put those weights, at what distance from the fulcrums, and realize that unless force equals distance on both sides of the teeter-totter, that is not going to balance. We were able to take that to the next level after they got an understanding of that and move outside with shovels, with wheelbarrows, with moving dollies, and they could actually see how what they learned and applied with a teeter-totter could be applied with other tools.
He makes everything simpler to where first he teaches it, and then if you don't get it, he'll spend all the time in the world with you to make sure you get it right.